We will be recording this part of the session. If anybody has any objections with the recording, please say so now. Okay, thank you. And so we're talking about the different types of test inputs that we have for modeling and analyzing dynamic systems. And so we had already found the mathematical models and transfer functions, in some cases, of different types of systems. We talked about the mechanical system, which is the mass, the first type of mechanical system, which was the mass spring system. Then we'd also talked about another mechanical system where besides the mass and the spring, we had added the dampener. And we had talked about three different types of circuit systems, RC, RL, and RLC. And we had also talked about the temperature transducer, and we'd gotten to a point in the temperature transducer where we have the mathematical model, but getting to a transfer function was a bit difficult. And we're going to circle back to that one in a bit. But let's talk about the impulse and how we could apply an impulse to the mechanical systems and see what happens. Let's do a refresher. Remember this system? This is the first mechanical system we had talked about, okay? And it's basically a mass that's connected to a fixed surface. And it's connected to the fixed surface using a spring that has a K constant. And we apply a certain force to the system. And because of the force we're applying, we generate a reaction, which is the distance that the mass is going to move. And we had already seen that the mathematical model for this would be represented by the differential equation that's ruled by Newton's laws. So the mass times the second derivative of the displacement plus the displacement multiplied by the K of the constant, which is going to be the force of the spring, is going to equal the force that's being applied. And so this is the mathematical model of the system, and we had already talked about that. From the mathematical model and applying Laplace, we had found the transfer function of the system. And what is the transfer function of the system? Or what does the transfer function represent? It basically, again, represents the relationship between the Laplace transform of the output and the Laplace transform of the input. And we had gotten something like this. And so now we have a system, which is the mass spring system, that has an input, which is the force that we're applying, that now we're calling it U of t. We could call it whatever we wanted to call it. And the output is x of t. This in the Laplace domain is U of s is going to be the input, G of s is going to be the transfer function, and x of s is going to be the output. And this is the transfer function that represents the behavior of the system. Now, question to the group. We had already talked about this system. And remember that we're trying to think about how real things behave, okay? How real things behave. So again, we've got a mass that's connected to a fixed surface with a spring, and we apply a force to it. Now, what type of force are we applying? Let's assume that the type of force we're applying to the system to see how it behaves is an impulse. Now, what would be an impulse? Imagine that the mass, imagine that this pink line here that represents the force, imagine that it is a piece of string. And so basically what we're doing is that we yanked the string. We just yanked the string. We yanked it and we let it go. That's what the impulse would represent. We yank the string, and that's the force I'm applying. Now, can somebody tell me, and we had already seen this example, can somebody tell me how the system, how do you think the system is going to behave if we do that? What's going to happen if we suddenly apply an impulse input, which basically the impulse would be that I'm just yanking the string, the pink line there. I just yanked it in an instant and then let it go. Let's see, we've got Daniel, we've got a couple of people raising their hands. I'm gonna go in order. So Daniel, go ahead and remember, please turn on your cameras if possible. So what do you think is gonna happen, Daniel? We'd already talked about this.
In terms of like,
Mhm. What is the system going to do? So it's a little, let's imagine it like a kind of like a cartoon. It's a little box with wheels. There's no friction. It's connected to a spring, and basically there's a string, and I pull it. I just yank.
So if there's no friction, then it's just gonna go like endlessly because there's gonna be like nothing's gonna prevent it like from going back and forth. But it's gonna be the same like force that you apply, which is that's gonna like go like in both ways.
Correct. And you said it very well. You said it's going to go back and forth. Okay. So if I were to plot that, if I were to plot this is time, and this is going to be the displacement x of t, then how would the response of the system how would the response of the system look like? Let me just use some colors here. Let's assume that the response of the system is going to be this x here. So it would go back and forth. And basically what we're going to have is something like this. And according to what Daniel said correctly, that's never going to stop. Why? Because there's no friction. Okay. Is that clear to everybody? We'd already talked about that. Is that clear that that would happen?
Yes.
Okay. So, but mathematically, and I want to come back to what the feedback that Ariane gave when we were asking the feedback about the mathematical part, because it's important to understand how we get to this and how we're going to be using math tools to get to this. But there's a mathematical way to get to this sinusoidal response. What would we do to get there? Okay, we've got the transfer function. Okay. So we have the transfer function, which is this function here. I'm going to write it down over here. We have the transfer function that says that g of s is equal to x of s divided by, which is the output that we're looking for, divided by u of s. And this is equal to 1 divided by ms squared plus k. Okay, that's the transfer function. Now, for this example, we are going to say that u of t, which is basically the input, is equal to the delta of Dirac. Now, I have u of s here, so I'm going to bring this over here and say that u of t is equal to, which is the input again, is equal to the impulse function, which is the Dirac delta. Now, by the way, this is a mathematical, the Dirac delta is a mathematical model that's already predefined. So if I want to represent an impulse, the function that represents an impulse is the delta of Dirac, which is this function here. Now, what I need is u of s. So I'm going to apply the Laplace transform here to this. So all of this. And so the Laplace transform of u of t is u of s. And this is where the way we're going to be using the math comes in. Somebody tell me what is the Laplace transform of the Dirac delta. How are we going to find that? There's a bunch of tables that we can use. Basically, any Laplace transform table that you can find has the delta of Dirac. Pablo, shoot, go ahead.
I think it's gonna be 1 divided by s because it's like a constant in a sense.
Be very careful with that, Pablo. It's not a constant.
It's not a constant, but it's like an instant.
Yeah, that's very, let's go with that, Pablo, because it's very important. In control system theory, there is a specific function that is the constant, and that has its Laplace transform. there is a specific mathematical model for the delta of Dirac that also has its Laplace transform, and they're actually different. Okay.
Okay.
So you probably, Pablo, let's go with, you're probably looking at a table, right? Or how did you?
Like, yes, I'm looking at a table, but
Mhm.
I remember like from when I saw Dirac that it was like similar to when you use like constants, like numbers, and you try to do the Laplace transform on that. So that's why I think it's one of S
It's one of
because of the
S.
instant.
If it were not an infinitesimal amount of time, which is the case of the Dirac, then it would be the transform of a constant. But in this particular case, and if you guys look at the Laplace transform tables, and I'm gonna you can find them online. If I switch over here, I'm gonna lose what I'm writing. But the Laplace transform of the Dirac delta, and actually you can Google it. The Laplace transform of the Dirac delta is equal to. Does somebody have it there?
1.
It's equal to 1. Exactly. And so this is important, Pablo, and the rest of the group. Yes, the delta of Dirac, it's like a constant, but it's a very specific type of constant that's occurring in a very, very small amount of time. And so there's a very specific mathematical model for that. And it's used in control systems and other areas, but for control systems. And it has a very specific Laplace transform. And so the delta of Dirac has a Laplace transform of 1. And so now that we have this, we're going to put this over here. And what we're going to get is the following. I'm going to write that down in a different color. We're going to have x of s divided by 1 is equal to 1 divided by ms square plus k. And I believe you guys would agree with me that x of s, in this case, because it's divided by 1, which is the output that I'm looking for, would be equal to 1 divided by ms squared plus k. Now, this is x of s for the input that I'm giving, but I really want x of t. So what would I need to do here? I need to apply the inverse Laplace transform to all of this. I need to apply the inverse Laplace transform to all of this function. Okay? And here's where the math part comes in. I would need to know the values of m and k, and I would need to apply the inverse Laplace transform of this. Okay? So remembering, does somebody remember the procedure we would have to follow to find the inverse Laplace transform of something like that? Just off the top of your heads from what you remember from differential equations? Anybody? Do you remember partial fractions? So we would need to probably apply some partial fractions there. Maybe in some cases, the Laplace transform is a direct transformation, which is this case here. Any model where we have a square plus a constant is going to give me as a result, the Laplace transform of this is going to give me a sinusoid. The inverse Laplace transform of this is going to give me a sine, which is basically what I'm looking for. Now, we can do all of the mathematical procedure, and we're going to take a bit of a time for that. This is a very simple example, actually. We can do the whole mathematical procedure for this. However, what we really want to be focusing on is on doing the analysis. Okay, so for those of you who like to do a lot of math, then you can work on this, and this can be a nice math exercise. But we're actually going to be taking advantage of the computational tools to be able to do this and to understand how systems behave and focus on the analysis part. And so I want to switch over to MATLAB to see how we can represent this and see how we can use MATLAB to simplify a little bit of the math that we're going to be doing. Okay. Before I do that, questions with this. This would be basically the general procedure we would follow if we were to find the analytical solution via an equation of the response of the system. But again, we want to be focused a little bit more on the analysis. So let's try to use some mathematical tools to be able to do that. So questions with this before I move on. Okay, keep the system in mind, please. Okay, and we are going to for the purposes of the analysis of the system, we're going to give the system some values. So we're going to assume that the mass is 1 kilogram, and we're going to assume that the K, the constant, is also 1 Newton per meter. Okay, so M is going to be equal to 1, and K is going to be equal to 1 also for the purposes of this example. Okay, I'm going to switch over to MATLAB. This isn't a lab exercise that we're going to be doing today. We're probably going to be doing the first lab exercise. We're probably going to be doing it when we come back. We're going to have some time there in the lab. However, if you want to follow along with me, either connecting to the computers at CETIS or in your MATLAB, then please do so. Okay, if you want to follow along with me. Okay, and regardless of that, the session is being recorded. So if you want to replicate this at another time, you can also do it. Okay, so I'm going to clear the drawings and I'm going to switch over to MATLAB. Okay, and please, you should be seeing the screen there, so you should be seeing my MATLAB. The thing here is that we're in a prompt here environment, so maybe the letters are going to be small, maybe not for you guys. But regardless of that, if you have any questions, please just raise your hand or unmute your microphones and go ahead. So, well, one thing right now we're going to be working in the prompt. Okay. We could do this in a program, but since we're only be doing a few lines, we can work in the prompt here also. For some of the lab exercises, I'm going to ask you to do a program that we just execute the program and does everything. But for right now, we're going to be working in the prompt. One thing that I usually like to do when I start off is I do a clear all. What does the clear all functionality do? Does anybody remember?
Clears variables, right?
Yeah, it clears the variables and any sort of, remember that MATLAB is like this big, huge calculator that can, so very good, thank you, Pablo. It's this big calculator that can do a bunch of things. And in MATLAB, you define variables, or variables are defined the moment you begin to use them. So the moment I start typing in here variables or any sort of a designation of words or letters or whatever, they start to be a part of the workspace and they stay there until I remove them. So we have to be a bit careful with that, because we might be working in the prompt and then suddenly we might be using variables that are already defined in the environment. So it's recommended to do that. Alfredo, please go ahead. You have a question.
Yes. What was the difference between clear all and CLC?
I think I don't remember. I think
CLC just clears the console, I think.
CLC clears the command window. So if I do this, CLC removes what's in the window. It's not removing the variables. Is the difference clear? So for example, if I say,
Yes,
I'm going to
yes.
say M equals 1, that M equals 1 now is part of the workspace. So if I say M, it's going to give me 1. If I do a CLC, it's going to clear the window, but M is still there. Okay. So let's say that you're using the workspace and you define variables and then you start doing something else, but the variables are still there. That could generate a problem. Okay. So the CLC is the other way. There's, I believe you can also do that with the right mouse button. There's a clear command window that you can also do. And so that's just so you don't have a bunch of stuff there. But it is important, the difference. Okay. You can actually clear some variables also, or all of them with the clear all. So I usually do a clear all. Okay. Is that understood, Alfredo? Is that okay?
Yes, thank you.
Okay, good. And so what we're going to be doing now, first off, I want to define in the environment the variables that I'm going to be using. And so right now we're going to be working with the mass the mass spring system. So basically there's two variables that I'm going to be using. By the way, I want to be careful not to confuse terms here. For MATLAB, they might be variables, but actually for the control systems terminology, these are parameters. Okay, so there's two parameters that I'm going to be defining: the mass, which I just said is 1. We can change that at a different time. And I'm going to be defining the K, which is also 1. Okay, M and K. Now, I mentioned before that if you're going to be using MATLAB, you need the MATLAB that has the control systems toolbox because it's the one we're going to be using. If it doesn't have the control systems toolbox, you're not going to be able to follow what we're going to be doing. So I'm going to be using a function that's part of the control systems toolbox. Okay, and that function that I'm going to be using is a function called TF. There's a couple of ways for you to know if the functions you're going to be using or the toolbox that has these functions are there. One is that you can just write down the function. So if I write down TF and put a parentheses there, do you notice that options appear? That means that that function is installed. Okay, that function is installed. The library where that function is, it's installed. If I click, for example, Sosa rules apparently isn't a function of MATLAB, and I click enter, it's going to give me an error. Okay. And it's telling me, did I mean Sosa rules? Of course I meant Sosa rules. That's what I wrote, MATLAB. But if I write TF, then TF, I do have the options. That means that TF does appear. Okay. I'm going to do a clear CLC. And just remember that M and K are still there. So I'm going to use TF. Basically, what the other way of doing it is just saying, for example, help TF. And what it's going to do is that it's going to tell me the different, what TF does and what does it do. Construct transfer function or convert to transfer function. So TF can be used to create a transfer function model or do a transformation of another model into a TF. We don't have to define the variable S or the S variable because it's already going to be part of the work environment as a variable. And so the MATLAB is object oriented and the functions are polymorphic. So what does that mean? It means that the functions can take on different versions according to how I give it the function, the parameters. So there's many ways in which I can create a TF or a transfer function using TF. The most basic one is the one we're going to be using here, which is TF num and den, which is the numerator and the denominator of the transfer function. Okay, the numerator and the denominator of the transfer function. And these are obviously given as vectors or matrices. Remember that MATLAB means matrix laboratory. Okay, the mat isn't math, it's MAT, it's matrix laboratory. So everything we do in MATLAB is based on matrices. And so what I'm going to do is I'm going to define a variable. And again, still M is here and K is here also. I'm going to define a variable, and this is just one I'm inventing, that I'm going to call sys. Sys, I'm going to make it long, just mass spring. And that variable is going to have the transfer function I'm going to define. And then I'm going to say that sys mass string is going to be equal to TF, which is a transfer function. And I'm going to define the numerator. I'm just going to write it down over here so everybody remembers. The transfer function that we are working with is G of S equals 1 divided by MS squared plus K. That's the transfer function we want to define. So the numerator for this transfer function is 1. Okay, so I need to change my keyboard. There we go. I'm going to define the numerator as 1. This is the vector representation of the numerator. By the way, if at any point I'm going a bit too quick or you have questions that have to do with refreshing MATLAB, please stop me. Or else I'm going to assume that that's not a problem and you're remembering some things. And the denominator in this case is going to be the vector that represents the polynomial in the denominator. So how do we represent that vector? It's going to be m, which is the first term, ms squared. What's the next term that would follow? Anybody? If I want to represent this polynomial here, I want to represent it as a matrix or vector with the coefficients. What would be, if the first one is m, what would the next one be?
S.
No, s is the variable. We're representing
okay.
and
Zero.
no, 0.
Oh,
Because the first element is s squared, the second element is s, and s isn't there, so it's a 0. And the third element is?
K.
K, correct. And so coming back over here, it's going to be M0K. We close up the parenthesis. I remember I used MATLAB at CETIS. I'm a cybernetic electronics engineer from 1992 to 1996. We began using MATLAB at CETIS with my cohort, with my class, with Nestor. Remember that Nestor is part of my class. We're classmates. We were the first engineering students that used MATLAB at CETIS. I remember there was a professor, Lucio Cheto, that he was coming back from his master's or doctorate. I think it was his master's studies. I think, yeah, master's should have been. And he was fluent. Him and his brother, they were very fluent in MATLAB. And we had a course, a programming course in 5th semester. This was 1994 in 5th semester, and he was teaching us MATLAB. But you know what? I already knew MATLAB. I was actually probably one of the first students at CETIS that worked with MATLAB. And I knew MATLAB because I had an opportunity to participate in the research, scientific research summer. I'm saying in Spanish, the Verano de la Investigación Científica. I did a stay at the UANL, the Universidad Autónoma de Nuevo León. And basically what I did there, and it was a very interesting experience, I was working with a professor that his research area was fuzzy logic. This was 1994, was fuzzy logic. And he said, you know what, I'm working with fuzzy logic. I need you to do a program that can help me, according to fuzzy sets I give the program, we need to be able to see the fuzzy sets and be able to graph them. And I need you to do that program. That's going to be your internship with me. And I'm like, Great, that's wonderful. I want to know about fuzzy logic. You're an expert on that, right? Yep. What do you want the program to be in? I want it to be in MATLAB. Oh, great, I'm going to learn MATLAB. Perfect. So are you going to teach me MATLAB? And he's like, nope. I want you to do the program. I can help you out with the fuzzy logic. I have no idea how MATLAB works. So I had to learn MATLAB by myself in about, well, the summer lasted 2 months. So in those 2 months, I had to develop a graphical program in MATLAB that could do the fuzzy logic representation. I don't even know what the program is or if it would run. I'd love to get that back. We're talking about floppy disks back then. So when I came back and I took the course, I already knew MATLAB. And I remember the professor, he was a good professor, but I know he didn't like me because I knew MATLAB. He was trying to teach MATLAB to the rest of the group and I was correcting him. And I know that was nice of me, but he was a very good professor, but I was not a very nice student back then, I think. And so I knew MATLAB before most of my classmates did. And MATLAB is hugely popular. That's why it's kind of like a second language and it's very easy to catch on, at least for me. And so what we've done there is we've defined the transfer function using TF, okay? Now what happens when I click enter if I don't have any sort of mistakes here? What are we gonna get? We're gonna get the we've already defined a model for a transfer function, okay? You see that? So what did we get here with the TF function? What we've done is that we have created a variable in MATLAB. We've created a variable in MATLAB, or an object rather. We've created an object, which is our mass spring system. This is basically G of S. And we've created an object in MATLAB that helps us represent that. Okay. Now, questions up to this point before we move on. Okay. So we've created an object in MATLAB that represents our transfer function. Now, this is where the power of computational tools in MATLAB comes about. We want to see how the transfer function of the mass spring reacts to an impulse. Okay. We want to see how it reacts to an impulse and maybe a step and maybe a ramp and maybe whatever type of inputs we want to give it. And we want to see how it reacts. We don't necessarily want to do all the math because that's going to take some time. We want to get into the analysis, and this is where these tools help out. And so, are there any questions with this before I clear the screen? Because I need to clear the screen because it's going to automatically clear when I type in something. So, no questions here? No. Okay. I'm going to clear the.
Nope.
I'm going to clear the drawings. And so, if there are functions in MATLAB as a part of the control systems toolbox that can help out with these sorts of things. So I'm going to do help impulse, which is the next function we're going to be using. And I get the help for impulse. By the way, another thing that I love about MATLAB, I love the prompt, the prompt where I can write. I come from a generation where our interactions with computers weren't through Windows or mouse based. So we had to literally type prompts to get things. By the way, you probably think I'm being inefficient here, but I'm actually not. I know we can go to a help tab and look for these things graphically. I like to do it here in the prompt because it's another way of doing it. It's a quicker way of doing it. So I know we can go here to help and find documentation, examples, whatever we want to do. I know we can do that. I like to do it here in the prompt. For me, it's more fun. So help impulse response to dynamic systems. So if I give the impulse function a system, it's going to plot the impulse response of the system. Okay. And there's many ways to use it here. So I'm going to click here, impulse, sys, what did I call it? Sys spring mass, did I call it? If I didn't call
Isn't
it
sysmass? It's on the left there on your workspace.
Oh yeah, thank you. Yeah, you're right. Thank you so much. It's your mass spring. Sys mass spring. Okay. And so if I click sys mass spring and I give it the impulse, what I'm going to get after some processing time here, I'm going to get this. This is the response to the impulse. Now, MATLAB is being, since I didn't give it any sort of parameters regarding how it was going to present it, MATLAB is giving me here a very, it's giving me 16,000 seconds here in the limit. I don't need that much. So I'm actually going to tell it to go from 0 to 10 seconds. And we've got this. This is a response to the system. Adrian, please go ahead. You've got a question or comment.
Yeah, just to say we can not see the figure, only the
Oh
prompt.
yeah, you're right. It is in another screen. Here we go. Let me do this again because I want you guys to see what was plotted, the original plot. Sorry about that. Let me do this again. Okay, there we go. Now I forgot that I needed to. It's a different screen, so I need to share it here. This is what I get. Now you see it? And thank you. I think it was Adrian or was it Adrian or Alfredo?
Yes, it was me, and we can see.
Adrian. Yeah, thank you, Adrian, for the note. This is what I get. This is the response. Now MATLAB is giving me from 0 to 1600. This is too much, so I'm going to say that I want from 0 to 10. And what do we get? This is the response of the mass spring to the impulse that I'm giving it. Okay, and I can, the interesting thing about this, I can select any point in the plot and see values. This is going to be important further on when we analyze the responses of the systems. We can see values here. We can look at other properties. We can give it a grid if we want. We can play around with this, and this is going to be practical and useful. Okay. So this is how the mass spring responds to a impulse input, or a very large input that is given in a very small time that would be yanking the string. Okay. Questions with this one before we take a quick break? No? Okay.
No, Professor.
Good. We're going to take a quick break and we will come back to continue doing some more examples. Okay, we're back. So, so this would be the response of the system if the spring mass system. This is the response of the system if we apply an impulse, which would be this pulling the string for an instant at the beginning when we start the analysis. And this is going to be the response for a mass of 1 kilogram and a K of 1 Newton per meter. Now, what can we see from this response? The period would approximately be period would be here, would probably be around 6.3 seconds approximately. That would be the period approximately here, 6.2. The magnitude, the highest or the peak value it gets to is 1. So that's information for a mass of 1 and a constant of the spring of 1 Newton per meter. Okay, what can I change in the system to change the response? So if I want a response that has different characteristics, maybe a different amplitude, maybe a different period of oscillation, what can I change in the system to change the behavior?
The friction, adding a friction.
Well, we're not yet talking about the friction situation. We're going to go to that one in a moment. Right now, we're just with this system. Let's see, Adrian.
Changing the parameters.
The parameters, correct. Which are the parameters, Adrian?
M and K.
M and K, correct. So right now, M is equal to 1 and K is equal to 1. Let's assume that I can't change the mass, that the mass is going to stay at 1 kilogram, but I can change I could change the constant of the of the spring. Okay, so let me close let's go back over here. And let's see how the system responds if we change these. So I'm going to now say M, I'm going to leave the same, and I'm going to say now that K, let's increase it. Let's double the amount of the spring constant. So now K is going to be equal to 2. I'm going to redefine the mass spring system. So now it's going to be equal to that. And I'm going to run the impulse again to be able to compare it. What do you think is going to happen if I increase the K of the, let's do a quick survey here. What is going to happen with the response if I increase the constant of the spring?
Shorter values.
Could you say that again, Miguel?
Shorter values.
Shorter values of what?
Well, I don't know, but K on the equation is on the bottom, so you'll be dividing by more stuff. So yeah.
Kind of, because remember that right now we're working with the transfer function. So we're not directly evaluating this. What MATLAB is doing when we create the impulse is that it's actually generating what we talked about mathematically. It's calculating the inverse Laplace transform, and it is evaluating the time domain of the function. Let's see, somebody else. What do you think is going to happen? Remember, you guys, I need you guys to think about the physical situation. What happens if I make the spring stronger? Pablo, go ahead.
There's gonna be like less displacement, I'm guessing, because since it's not like if you apply the same force and it's like it has more resistance, it's not gonna be being pushed all the way, and the movements are gonna be like shorter instead of being like longer, perhaps.
Yeah, because the spring is stronger. It's generating a more stronger force than the one we previously analyzed, which was 1 Newton. So good observation. Let's see what happens. I'm going to switch screens. I need to remember about this. We get this response. I'm going to put the same time I did with the other one. And what do we notice with this one with regards to the previous one? What happened to the period?
They got shorter or like lesser.
What was the previous? Did somebody remember what the previous period was?
2.6.
Yeah, 2.6. Good catch there, Ariane. So actually the period got longer. So the distance got shorter and the period got a little bit longer. What happened with the magnitude, which has to do with what Pablo was saying?
It's lower.
It's lower. It's a smaller amplitude. So the maximum here is roughly around 0.707 approximately. Is 703, something like that is the maximum, 7.7. So instead of going 1 meter, now it's going 0.7 meters. Okay, and the period is shorter. So again, think about the physical system. When the parameters were 1 kilogram of mass and 1 Newton per meter, and we pulled it, it oscillated 1 meter back and forth because the units are in meters. It oscillated 1 meter back and forth, and it had a period of I think Ariane mentioned it, 2.6 or something like that. Now, when the spring is stronger, the mass is now, like Pablo mentioned, isn't going further. It's going slower. It's going shorter because the spring is stronger. Now let's see what happens if we increase it. Oops, stop sharing. A moment. Now let's assume that we decrease the K. So instead of being 0.2, now it's going to be 0.5. And we're going to redefine the system. Oops, we're going to redefine the system now with the 0.5, and we're going to graph it and see what happens. When the spring is weaker than the first reference, since the spring is weaker, now it's going above the 1 that was the original reference. Now it's going around 1, close to 1.41 approximately. And we've actually have a longer period here. Let me put this at 20. We have a longer, even longer period now, okay? And so we see the effect of making the spring weaker or stronger, depending on the system. This is very important, you guys, because what we're gonna be doing is that we're gonna be analyzing systems, and we're gonna be relying a lot on software like MATLAB to be able to do that. And what we're gonna be seeing is that we need to be able to interpret the graphs that we're gonna be seeing, and interpret the graphs regarding the parameters that we're going to be doing, we're going to be using. Okay. Now, okay, forget that it's 2 windows. Sorry about that. Okay, now questions with this one before we look at another example. Okay, now let's talk about the other system we had, which is also a mechanical system. We had the same mass system with a K and a certain mass here. We also applied a force here. And we also got a displacement. But the difference here is that we had added another variable, another parameter, which was the friction. And we had added that as what we call a dampener. And if you guys remember, and this is in the PowerPoint in the notes, we had already found the transfer function for this. I'm going to write it down here by memory, but please verify so I don't make a mistake. So G of S, I believe, was equal to, and this was actually in the exam, 1 divided by MS squared plus BS plus K. Is that the one we had found? Please check just to see if you guys are awake. I believe it was.
It is.
Okay. So now let's assume that we have got this system, and now we've added a dampener that represents friction. Okay. So it's the same situation. I've got a string here and I pull the string. Can somebody tell me how that system is going to behave? And we had already talked about that. How would that system behave if I yank the string? But now I've got friction. Anybody?
Same way, but it will slowly start to cease motion after
Correct.
time.
Correct. Perfect, Miguel. Perfect. So it's going to be the same. It's going to react. It's going to want to react the same way. It's going to want to move, and then the spring is going to want to pull it back. However, the difference with the previous one is that the friction is going to make, every time it pulls back and goes forward, the friction is going to remove energy and is going to make it, eventually, the oscillation is going to stop. So that's what we should see for this system. So let's see how we can use MATLAB to define that. So I'm going to also, for the purpose of the example, I'm going to say, I think I had already done a clear all. I'm going to say that the mass is going to be equal to 1. I'm going to say that the B is also going to be equal to 1, just for the purpose of the example. And the K is going to be equal to 1. Okay. And I'm going to say cis mass damp. I'm going to call it cis mass damp system, is going to be equal to transfer function of the numerator, which is going to be 1. How would the denominator be defined? Anybody? How would I define the vector for the denominator for that transfer function?
I'm guessing M1 and 1 maybe, or M1 and K, or well, MB and K.
Correct. If we were to use the constants, Pablo, it would be M1, 1, and 1, but we've defined it over there, so we're going to say MB and K. Okay. So very good. Remember, I'm noticing who's participating. So remember, if you don't participate, I'm going to call on you probably on Wednesday. Okay. This is like my daughter's kindergarten class. On one day, they've got the students participating, and if you don't go on that round, the next day they're going to call on you. Okay. So remember, I'm taking note of who's participating and who's not. So please ring in. And so if we define it like that, and assuming that there isn't any errors, then we've got the system defined there. Sorry about that. So we've got 1 divided by s squared plus s plus 1. And so what we're going to do here, I'm going to also call upon the impulse function of cis mass damp. And let's see what happens. I'm sorry, let's see what happens there. Let me switch screens here. And we get this here. We get the response of the system. So what do we notice here in this response? When we pull the string, the mass is going to jump forward to a certain maximum value, then it's going to go down, and then eventually it's going to stop the oscillation. Okay. What's important to note here is that if we were to solve this equation mathematically, the model for this is going to be an exponential multiplied by some sort of sign. So it's an oscillating behavior that decays exponentially. Okay, and that's the behavior of a typical second order system. Okay, now, okay, questions up to this point before we move on, and I start asking you some questions. Let's see, Ariane. Ariane, let's see. So Ariane, let's think that this is a response to the system. Okay, so we had already understood that the little box is going to go forward, and then eventually it's going to stop, right? So that was that part clear?
Yes.
Yes, and is it clear also that the graph represents that, right?
Yes.
Okay. Now, put on a cap that now you're a control systems engineer. Okay. Forget about anything else. You're trying to analyze this system because you want it to behave differently eventually. So, Ariane, tell me what would be of interest to you in the analysis of the behavior of this system. What would you're looking at the behavior, and maybe you're looking at it, but now you're not looking at it. You're looking at the graph. What would be things you take note about how this system is behaving that might be of interest further on?
Like what information is interesting on the graph?
Mm-hmm.
Okay, I will take like the biggest point in here, like the amplitude. I call it amplitude. I don't know, magnitude. You mentioned, right?
Mm-hmm. Yeah, perfect. No, amplitude and magnitude, both are correct. Both are correct. Perfect. You want to know the largest value, the furthest the little box goes away from the part. That's with reference to the magnitude or amplitude. That's perfect. That's obviously something we need to know. In control systems terminology, we're going to call that, and for you guys to take note, we're gonna get into that later on, but in control systems terminology, Ariane and the rest of the group, we call that the peak response.
Peak.
Okay, so you say, okay, it's of interest to me to know the highest point or the largest displacement that it has. Well, the graph is going to tell us that, and it's this point here. And actually, the good thing about MATLAB here in this graphs is that we can actually just click it and it's going to give us this information. If we were to do this manually, we would need to do the Laplace transform, find the equation, then graph it and see what's going to happen. And we can do that, but we want to, right now we've got our control systems engineering graph. So good, Ariane. What is the peak amplitude that we see there? Approximately.
5.4.
0.546. By the way, again, we're in the analysis part. Ariane, what units are those? You think?
That's distance, right? Like meters or feet? Maybe.
We're talking about kilograms, so these are meters. Okay.
Meter.
And it's important. It's very important. I want to get you guys in tune that we need to look at the graphs and look at the numbers and relate them to the. So they're meters, and it's distance, or in this case, displacement. So these are meters. Perfect. That's something that's of interest to us. Okay. Perfect. Well done, Ariane. Thank you very much. Let's go with Angelica. Are you there, Angelica?
Yes.
Okay, Angelica. Now, again, we're with our control systems engineer CAP. Okay. So Ariane mentioned one thing that's of interest that I would take note of is the amplitude. That's data that I need to analyze to see how the system behaves. Can you think of something else that might be important to note in how the system is behaving if we want to eventually modify that? So we've already said the amplitude, the peak amplitude. What else do you think would be of interest?
I want to say like the consistency, like the frequency of how it moves.
The oscillation? Are you,
Yeah.
yeah, because it's oscillating anyway. So even, yeah, I just turned into I switched to Spanish and Fresón. I'm sorry about that. So what I mean, so even if the system is stabilizing, there's some sort of oscillation because we've got a little wave here. Okay. So yeah, we might want to know something about the frequency of this oscillation. That might be of interest because right now this oscillation is very slow, but it might be a very quick oscillation and that might affect. Okay, good, thank you, Angelica. Let's see, Carlos. The more people I call on, the further we go, it gets a little bit more difficult because you're having less things to analyze. But so Ariane has mentioned the peak amplitude, which is the maximum value it gets to. Angelica mentions, well, I might want to know a little bit about the oscillation or the frequency. Anything you can think about that might be of interest to note?
How much time it takes to get back to its natural state?
Perfect. That also has a name in control systems terminology. Okay, and what I want to say about what you mentioned, Carlos, is that we're always interested in the when. Okay, so the time is very important. So that that characteristic of the system, it's called the setting time or the settling time. And actually, it's something that we can also obtain its control systems terminology. it's called the settling time. And here it is. What time is the setting time there, Carlos, approximately?
9.29 seconds.
9.3 seconds. Now, here's the thing. Is it exactly in zero at that time, Carlos? Roughly from what you can see?
I don't think so. It even goes like beneath zero after that, I think.
Yeah, it's not exactly at zero. So why is MATLAB telling me that that is the settling time? Well, because in control systems terminology, the setting time is going to be defined as the time it takes the system to stabilize within a certain range. So I'm going to repeat that. So if you guys, we're going to formally give these definitions, but you guys better be taking note. The setting time is going to be the time it takes for the system to reach a stable state within a certain range. And for example, if I go over here to properties, I think it's here. Yeah, what do you see? I don't know if you can read here. This is, don't know how small it is, Carlos, but what do you see here? If you can read that.
Settling time within 2%.
I can play around with that. So MATLAB, the parameter that MATLAB is giving me for the design, for the analysis criteria that you established, Carlos, it's saying, okay, we're going to consider that the system is stable or it's reached the zero within 2% of the value of the stabilizing value. So actually, if we measured that, that's going to be, since it's zero, it's probably going to be 0.2 and minus 0.02 and minus 0.02. I can play around with this and I can say I want more precision. I want this to be, I'm going to really exaggerate, 0.1%. And there it goes. We went to 13.9 over here. Okay. We can play around with that. Eventually, we're going to get to some mathematical formulas that define these things. But usually in control systems, it's not random that MATLAB put this at 2%. Okay, it's not random that it put it at 2%. Why? Because in control systems theory, we usually talk about the setting time between 2 and 5%. Okay. Okay. Good job, Carlos. Thank you very much.
Professor,
yes, go ahead, please.
may you repeat the settling time definition?
The definition. Okay, setting time. What would, and remember that all this is being recorded, so you guys can go through the video later also. So the setting time, well, let me give most of the definitions I've given up to this point. The peak value is going to be the maximum value that the response has once a certain input is given. And that's a reference, so it can be the maximum or the maximum can actually be a minimum, but it's the highest or lowest value that the function takes. And then the setting time. The setting time is going to be the time it takes for the system to reach stabilization within a certain range. Now, it's important, the stabilization part, because remember the previous example where it was oscillating? That didn't have a peak time or a setting time. Why? Because the oscillation, the continuous oscillation that we had in the previous example where we didn't have the dampener, technically that's not a stable system. Technically, that's not a stable system. It's called marginal stability. And so the cool thing about these graphs is that they're being able to tell me this information. Okay. Okay. Questions with this before I'm going to ask one more person. Oh yes, go ahead, please, Carlos.
Is it setting time or settling time?
It's that's a very good question, Carlos. It's settling time. Settle, like yeah, like settle. S-E-T-T-L-E. So it's kind of those words where you say it, or I say it quickly and I say setting time, but it's settling time because it's the time it takes for the response to settle. Okay, so it's settling. I sometimes say it as setting because I miss the L, but it's settling time. Okay.
Okay, thank you.
Okay, good. Any additional questions? I'm going to pick on one more person, and I'm sorry because you've mostly already, Ariane, Angelica, and Carlos already said most of the things we're interested in. So I'm going to pick on one more person, and I'm going to even try to help them out and give them a hint. Let's see, Josue, go ahead, please. I think you're muted, Josue. Go ahead, are you there? You'd raise your hand.
I was my oh, sorry.
Yeah,
I have an idea, but I'm not sure if it's okay.
Go ahead, shoot.
Probably the lowest peak, like the lowest amplitude.
Yeah, that could, so we can have the peak value, which is the highest point, and we might also want to know the lowest point. That's a good observation, Josue. There's actually a couple of more things, and you mentioned one of them. So another thing would be this lowest point here, okay? Why would the lowest point be of interest? Because remembering that we're talking about distance, so it's oscillating going forward and going backwards. The reference is going forward, but we might want to know what is the lowest. In this case, the lowest value isn't a lowest value. The lowest value here, because we're talking about displacement, the lowest value is really when the box goes to the other side with regards to its zero reference. So the positive is when it goes forward, the negative or the lowest would be when it goes backwards, okay? So that might be another thing to consider. Good catch there. Good.
Thank you.
The lowest. Let's see. Luis. You've not been left with anything here, Luis. But what could be one other thing that we're interested in? And I'm going to give you a hint. It's already here in the graph. And I'm going to get, just because you were left with the tough, I'm going to kind of give you a hint. What else could we also be interested in?
Is that peak amplitude the hint? Like
No, that's what Ariane mentioned, which is the amplitude.
Oh.
So
The times of the where the peaks happened and the lowest happened.
Exactly, the times of everything. So we're not only interested in the highest value, we also want to know when it occurs. We're interested in the lowest value, we want to know when it occurs. We're interested in the settling time, we want to know when it occurs. Why is that? Because we want to know if the reactions of the systems are slow or fast, or too slow or too fast. Okay, that's going to be important. So I'm going to ask you guys a question. This is an open-ended question, whoever wants to answer. Look at the response of this system, the mass spring dampener system. Is the reaction of this system slow or fast?
Slow.
It's slow. Why? A couple of you answered slow. Why do you think it's slow? Give me your reasoning for that. Marianne, I think you commented. Go ahead. I think Marianne is frozen. I think also somebody else, I think Luis had also mentioned something. Oh, Marianne, you were frozen there for a moment. Go ahead. Yeah, we can see you now.
Just confirming.
Yeah.
I think it is low because it lasts like 14 seconds, which I think it is a lot.
Yeah, and the setting time is almost 10 seconds. 10 seconds is an eternity. Now, is it slower? That with regards to that, I think your assessment is correct, Marianne. It's slow. But maybe we want it to be slow. We don't want a very, very quick reaction. Marianne, I always pick on you because you're the part of who I identify as you and a couple of your other friends, but you're the robotics, CFOX, line followers gurus here. So remember when we talked about the line followers? And remember that there was a trade-off between precision and speed? We're always playing with those trade-offs. So maybe I want the system to be extremely precise and careful. And so you've got your line follower and it's following the lines precisely, but it's taking a long time to do it. But you want precision. That's your main criteria. So it doesn't matter if it's slow. Maybe you're going to get points for finishing the maze quicker. And so you're not that interested in precision. You want it to be quicker. In that regards, this system is extremely slow. What I'm trying to get at is, depending on your design criteria, is how you're going to interpret if the system is slow or not. I would say this system is slow because 10 seconds to stabilize is a long time. Okay, so I would say that's correct. Even to reach the peak amplitude, it's going to take 1.2 seconds. That's even a long time. But it's going to depend on the reference you guys are taking. Okay. Questions with this example before we move on to some other things? Nope. Okay. I'm going to close. And so the important thing here with MATLAB and these graphs is that we're going to be able to. Oh, Luis, go ahead, please.
It's just one question or a request. Can we like increase the value of M so we can see how the behavior changes?
Yeah, that's a good observation. We're actually going to do this, Luis. It's good that you, Luis and I aren't coordinated, so he isn't a teaching assistant in my class or anything like that, but you actually did a good segue to do a variation of this. So let's do the following. I'm going to clear this and I'm going to close this window. I'm not going to close the window. I'm going to switch to share because if I close the window, we're going to lose that. Give me a moment. Here we go. We're going to do something here based on Luis's question. Let's hope I don't muck it up. I'm going to do a clear all just for the purposes of doing this in a CLC. Okay, I'm going to do this. Let's imagine that we have two different types of systems. We've got, let's vary one of the parameters, okay? Which is the mass, which is what you mentioned, Luis. Let's assume that we vary the mass, but we leave the other two as they are. Would that be okay? So let's say that I've got mass 1 equals 1 kilogram, and let's do 3 variations. Mass, I'm going to say mass 1 is 0.5, mass 2 is equal to 1, and mass 3 is equal to 2. Okay, we've got 3 situations there. I'm going to be even more exaggerated because maybe we're not going to be able to see the difference. I'm going to say that mass 1 is 0.1, mass 1 is 1, and I'm going to say mass 3 is 10. Okay? I'm going to leave B and K exactly the same. Okay? B is going to be equal to 1, and K is going to be equal to 1. And I'm going to define 3 systems. Okay? I'm going to define 3 systems. Sys mass damp 1, which is going to be 1, M1, B, and K. Right? I'm going to define sys mass damp 2, which is going to be M2, B, and K. And I'm going to define sys mass damp 3, which is going to be M3, B, and K. Okay? Are we okay up to that point, everybody? And Luis?
Yes.
And so you're still there, right, Luis? I just want to check if the those people that when you're playing multiplayer and you're playing zombies or you play whatever, and they just kind of grab the grenade and throw it and then just go away. So I just want to check if you're still there, Luis. So it's a very good example, but we're doing this because we of your question. Pablo, go ahead.
I have a MATLAB question. How can I call like variables when you were like copying sys mass temp?
Oh,
Like how do you do that?
oh, this that I was doing?
Yeah.
Oh, okay. I'm sorry because you can't see what I'm doing there, Pablo, is that in the prompt, I'm pressing the up arrow.
Oh, okay.
When you press the up arrow, it's giving you, the up arrow gives you the history of everything you've written down. So it's really practical because you can just go back and grab something and just modify it. So it's up arrow. There's probably another way of doing it. I do it with the up arrow.
Okay, thank you.
And now what we're going to do is I'm going to say impulse. I really don't remember if I can do this. So I think it does support this. What I'm going to do is give the impulse function the three systems, I'm sorry. I think I can do this. So I'm going to give the impulse function the same one I was using, but I'm going to give it 3 systems. And what it should do, if it's not an error, I don't remember, this might not work, by the way. I don't remember if this supports it or not. It should graph the 3 responses in the same window. Ah, there we go. There we go. Let me switch over here. And now we've got this. Let's see the color coding here. By the way, this is when you click the right mouse button, and here in systems, when you have more than one, you've got the color code. So the mass of 0.5 is the dark blue. The mass of 1 is the red, and the mass of 10 kilograms is the light brown, which kind of looks orange in my here. I'm going to modify the time because 140 seconds is too much. I think I can give it around 40. I'm going to give it 40 seconds. I'm going to give it, well, I'm going to give it 60 seconds. Yes, go ahead, Ariane.
It will be better at 80.
80, right? Because of the setting time of the third one.
Mhm.
Yeah, you're right. Because the setting time of the third one is the one that's longest. Yeah, 80 would be better. Good. Thank you, Ariane. There we go. Notice the 3 responses. We've got 3 different responses. Which of the 3 is the quicker response? I've got 3 masses. Let's say the light mass, the medium mass, and the heavy mass. In which of the 3 masses the system responds quicker or faster?
The blue one.
And again, I'm sorry to be poking you guys, but we don't have a blue mass, a red mass, and a brown mass. We have a light mass, a medium mass, and a heavy mass.
The light mass.
The light mass.
The light one. And why am I saying light, medium, and heavy? I need you guys to relate to something that's light, something that's heavy, something. So the mass that's lighter is the one that has a larger, if we go to the peak response, the lighter mass has a peak response of the largest amplitude of 0.835. Then we've got the next one that's 0.546, and the third one, which is the heaviest one, 0.252. Is that logical to you guys? Wouldn't it be logical that the heaviest mass, the orange one, the 10 kilogram, would be harder to move or displace? Does that make sense to you guys? The lighter mass would be the one that you could move more, okay?
Yes.
And then we've got the setting times. We can also see the setting times for the 3 situations. So the light mass, we have a setting time of 3.86. Then we've got the heavier mass with 9.29. We'd already seen that. And the heaviest mass, we've got a longer setting time of 77.7 because we've also got inertia. Remember that? Why would the heavier mass take longer to settle? It's got more inertia. Okay, do you see that? The lighter mass has less inertia. The medium mass has a bit more inertia. The heavier mass has even more inertia. It goes less further, but it's going to take less time to settle. Okay, does everybody see that?
Yes.
This was a good example. Is Luis still there? Because he kind of threw the grenade, and I just want to see if this was clear. Luis, are you there? I'm going to pick on you.
Yes, sir.
And remember, please don't send a letter to Professor Capiz or Nestor or Dr. Solari. I'm not picking on you, picking on you guys negatively. This was a very good question that you made, Luis, and it's actually a very good example to be able to see how when I change the mass, the behavior of the system changes. Okay. Remember when we talked about when we're balancing the tires, what we do, we're actually adding mass or removing mass from the tire. It changes the behavior. Okay. Questions with this before I mention one last thing before we wrap it up. Now, remember that the transfer function was g of s equals one divided by ms squared plus b plus bs, I'm sorry, plus k. And so the value I was changing was this one in the three situations. Now, what we're going to eventually get at is that this equation that we have in the denominator is going to be hugely important in a transfer function. This is called the characteristic equation. First question, this is a math question. What order is the polynomial in that I marked there in green? What is the order of that polynomial?
Second.
Second order, perfect, Maria. How many roots does that polynomial have?
2.
Are the roots imaginary or real or a combination of both of those?
It could be a combination of both.
Exactly. The answer is, for the last question I asked, the answer is we don't know. It depends on M, B, and K. And so what we're going to eventually get at is the roots of this polynomial. And the roots are going to be defined by these three values. Are going to directly have to do with the behavior of the system. So by finding the roots of the polynomial, or I know how the system is going to behave. Just by finding the roots, I can tell you how the system is going to behave. But also, if I modify those roots, and actually by modifying the m in what I'm going to call Luis's example, by modifying the m, we have modified the roots. And by modifying the m and modifying the roots, we were able to modify the behavior of the system. Okay? Think about that. That's what we're eventually going to get to. Okay? Questions with this before we wrap up?
No.
Okay.
Not right now.
Okay, good. So